NEC Section 250.45 mandates that a grounding electrode conductor must connect to the equipment grounding conductor either at the generator itself or via a separate ground rod placed at the generator's location. This grounding practice is crucial, especially when a generator serves as an alternative power source through transfer switches. The primary reason for grounding the generator stems from the necessity to ensure the generator's grounded system, specifically the neutral point in a delta-configured system, is effectively bonded to the building's overall grounding infrastructure. This bonding yields significant benefits. Firstly, electrical safety is greatly enhanced. A properly installed ground wire provides a reliable path for current to flow in the event of a fault condition. This directed flow prevents the buildup of dangerous voltage levels on equipment surfaces, mitigating the risks of electrical shock and potential fire hazards. Secondly, proper operation of both the generator and any connected equipment is facilitated. The ground wire aids in stabilizing voltage levels, ensuring that the generator functions within its intended parameters and that the equipment it powers operates reliably. Thirdly, code compliance is achieved. NEC Section 250.45 explicitly requires grounding for generator installations, making it a non-negotiable aspect of any compliant setup. Conversely, failing to establish a ground connection from the generator can lead to a cascade of problems. The absence of a ground significantly elevates the risk of electrical shock and fire. Without a dedicated ground path, fault currents may not be properly directed, leading to dangerous voltage potentials on accessible equipment. Improper operation of the generator and connected equipment can also occur. A stable ground reference is essential for many electronic devices to function correctly, and its absence can lead to erratic or unreliable performance. Naturally, a lack of grounding constitutes a violation of the NEC, potentially leading to fines, project delays, and increased liability in the event of an incident. Addressing cost considerations is important. Implementing a ground wire from the generator, especially over longer distances, can represent a substantial expense. However, viewing this cost as an investment in safety and code compliance is crucial. Several strategies can help mitigate the financial impact. Firstly, explore the possibility of utilizing existing conduit or other pathways to minimize the need for extensive trenching and excavation. Secondly, consider installing a grounding electrode system directly at the generator's location. This approach may eliminate the need to run a long ground wire back to the main building ground. Thirdly, engage in negotiations with the contractor to identify cost-effective solutions that still meet the NEC requirements without compromising safety. In conclusion, while the cost associated with running a ground wire from the generator might seem significant, it is an indispensable measure for ensuring the safety and reliable operation of the generator and the equipment it serves. Given that NEC Section 250.45 mandates grounding for generator installations, adhering to these regulations is the responsible course of action, helping to minimize electrical hazards and maintain code compliance. When dealing with a 480-volt delta system, understanding the grounding requirements becomes even more critical due to the higher voltage levels and potential for increased fault currents. The absence of a neutral connection in a standard 480-volt delta system means that a ground fault can go undetected, leading to dangerous voltage buildup on equipment. Running a ground wire from the generator to the building's grounding system provides a low impedance path for fault currents to flow, tripping circuit breakers and clearing the fault quickly. This is essential for preventing electrical shock and fire hazards. Several factors influence the size and type of grounding conductor required for a generator installation, including the size of the generator, the length of the conductor run, and the type of grounding electrode system used. NEC Table 250.122 provides guidance on the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. For long runs, it may be necessary to increase the size of the grounding conductor to minimize voltage drop and ensure adequate fault current carrying capacity. The grounding electrode system for a generator should be installed in accordance with NEC Section 250.52. Common grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The selection of the appropriate grounding electrode system depends on the soil conditions and local regulations. In some cases, it may be necessary to install multiple grounding electrodes to achieve the required grounding resistance. When connecting the grounding conductor to the grounding electrode, it is important to use approved connectors and follow proper installation practices. Improper connections can increase the resistance of the grounding path, reducing its effectiveness. It is also important to protect the grounding conductor from physical damage and corrosion. In addition to the equipment grounding conductor, it may also be necessary to install a grounding electrode conductor to connect the generator frame to the grounding electrode system. This conductor helps to ensure that the generator frame is at the same potential as the earth, reducing the risk of electrical shock. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the largest ungrounded conductor in the circuit. When installing a transfer switch, it is important to ensure that the grounding conductors are properly connected to both the normal power source and the generator. The transfer switch should not interrupt the grounding conductor, as this can create a dangerous situation. The grounding conductor should be continuous from the power source to the load, providing a low impedance path for fault currents to flow. In some cases, it may be necessary to install a separate grounding conductor for the generator to ensure adequate grounding. This is particularly important for long runs or when the normal power source grounding conductor is not adequately sized. When working with generator installations, it is important to consult with a qualified electrical contractor to ensure that all NEC requirements are met. A qualified contractor will have the knowledge and experience to properly size and install the grounding conductors, grounding electrodes, and transfer switches. They can also perform testing to verify that the grounding system is functioning properly. Neglecting the grounding requirements for generator installations can have serious consequences, including electrical shock, fire, and equipment damage. By following the NEC guidelines and working with a qualified electrical contractor, it is possible to ensure a safe and reliable generator installation. It's also worth considering the impact of harmonics on grounding systems. Nonlinear loads such as electronic devices and variable frequency drives can generate harmonic currents that circulate in the grounding system. These harmonic currents can cause overheating of grounding conductors and equipment, as well as voltage distortion and interference with sensitive electronic equipment. To mitigate the effects of harmonics, it may be necessary to install harmonic filters or to increase the size of the grounding conductors. It is also important to ensure that the grounding system is properly designed to handle harmonic currents. Another important consideration is the type of grounding system used. There are several different types of grounding systems, including solidly grounded, impedance grounded, and ungrounded systems. The type of grounding system used will affect the way fault currents flow and the level of protection provided. Solidly grounded systems provide the lowest impedance path for fault currents, resulting in faster fault clearing times and lower voltage potentials. However, they can also result in higher fault currents, which can damage equipment. Impedance grounded systems use a resistor or reactor to limit the fault current, reducing the risk of equipment damage. However, they can also result in slower fault clearing times and higher voltage potentials. Ungrounded systems do not have a direct connection to ground, which can reduce the risk of electrical shock. However, they can also make it difficult to locate faults and can result in overvoltages. The selection of the appropriate grounding system depends on the specific application and the level of protection required. It is important to consult with a qualified electrical engineer to determine the best grounding system for your needs. Regular inspection and testing of the grounding system are also essential to ensure that it is functioning properly. Grounding conductors should be checked for corrosion, damage, and loose connections. Grounding electrodes should be tested to verify that they have a low resistance to ground. Transfer switches should be inspected to ensure that they are properly switching the grounding conductors. Any problems with the grounding system should be corrected immediately to prevent electrical hazards. By following these recommendations, you can ensure that your generator installation is safe, reliable, and compliant with the NEC requirements. This comprehensive approach to grounding not only addresses immediate safety concerns but also contributes to the long-term performance and reliability of the electrical system. Remember, proper grounding is not just about meeting code requirements, it's about protecting people and equipment from the dangers of electricity. Therefore, investing in a well-designed and properly maintained grounding system is a worthwhile investment that pays dividends in safety and reliability. Considering specific applications like data centers or healthcare facilities, the criticality of grounding becomes even more pronounced. In these environments, even momentary power interruptions or voltage fluctuations can have catastrophic consequences. A robust grounding system is essential for maintaining the integrity of data, protecting sensitive medical equipment, and ensuring the safety of patients and staff. For instance, in data centers, the grounding system must be designed to minimize electromagnetic interference, which can disrupt data transmission and cause equipment malfunctions. Similarly, in healthcare facilities, the grounding system must be designed to prevent leakage currents, which can pose a serious hazard to patients with implanted medical devices. In these critical applications, it is often necessary to go beyond the minimum NEC requirements and implement more sophisticated grounding techniques such as isolated grounding systems or equipotential bonding. These techniques help to create a low impedance path for fault currents and minimize voltage differences between different pieces of equipment. The use of surge protective devices is also crucial in these environments to protect sensitive electronic equipment from voltage surges caused by lightning or switching transients. Surge protective devices divert surge currents to ground, preventing them from damaging equipment. In addition to the technical aspects of grounding, it is also important to consider the human factors. Electrical workers should be properly trained in grounding procedures and should always use appropriate personal protective equipment when working on electrical systems. Regular safety audits should be conducted to identify and correct any potential grounding hazards. By combining technical expertise with a strong safety culture, it is possible to create a safe and reliable electrical environment in any facility. Furthermore, understanding the different types of grounding electrodes and their applications is crucial for effective grounding. Ground rods are the most common type of grounding electrode and are typically used in residential and commercial applications. They are driven into the ground to provide a connection to earth. Ground plates are used in areas where it is difficult to drive ground rods, such as rocky or sandy soil. They are buried horizontally in the ground to provide a larger contact area with the earth. Concrete encased electrodes, also known as UV grounds, are embedded in concrete foundations to provide a very low resistance ground connection. They are often used in new construction projects. Underground metallic water pipes can also be used as grounding electrodes, but only if they are in direct contact with the earth for at least 10 feet. Plastic water pipes cannot be used as grounding electrodes. When selecting a grounding electrode, it is important to consider the soil conditions, the size of the electrical system, and the local regulations. In some areas, the local electrical inspector may require a specific type of grounding electrode. It is also important to ensure that the grounding electrode is properly installed and maintained. Ground rods should be driven deep enough into the ground to reach moist soil. Ground plate should be buried below the frost line. Concrete encased electrode should be properly bonded to the reinforcing steel in the concrete foundation. Underground metallic water pipe should be inspected regularly for corrosion and damage. By paying attention to these details, you can ensure that your grounding system is functioning properly and providing the level of protection you need. In summary, grounding is a critical aspect of electrical safety and should not be overlooked. By following the NEC requirements, working with a qualified electrical contractor, and implementing a comprehensive grounding strategy, you can protect people and equipment from the dangers of electricity and ensure a safe and reliable electrical environment. It's a multifaceted subject involving code compliance, technical expertise, and a strong commitment to safety.